Good afternoon, everyone. We are here to present our Smart Campus Simulation project as a part of the Software Engineering and Project Management course. So, our team members are myself, Siri Vishwanath Hegde, Harshita R, Mohit UK, Mukund V, Amog V, Preyas, Nityashree Iyer, Raman, Nidhi Vijay Shinde, and Dev Kukreja. So, in this presentation, we will briefly walk through our project idea and how we applied software engineering principles while developing it. I will be covering the overview about the project and the requirements engineering part as well, which helped us clearly define the system before implementation. Going on to the, this slide itself. So first I'll tell about the project. So our project is like a prototype of a smart campus environment. The main idea is to monitor real-time conditions in a campus, such as temperature, humidity, light, motion, etc., using IoT sensors connected to a Raspberry Pi. Now, the collected data is sent to a central dashboard where administrators can view and analyze the campus conditions. So, this kind of system can help in improving energy efficiency, safety, and overall automation as well within educational institutions and other campuses. Essentially, it simulates how a real campus would function, but on a smaller scale that we built and we can test it as well. Now, I'll talk about the requirements engineering part. So, before building the project, we followed the requirements engineering process to clearly understand what the system needs and how that should work. So, the functional requirements define the main features of the system, thus collecting the sensor data and then sending it to the monitoring system and displaying it on a dashboard as well. So, the non functional requirements focused on the quality aspects. For example, the system should update data in real time. The communication should be secure, it should be reliable as well, and the dashboard should be simple and user friendly. So, by documenting all these requirements in an SRS, we had clear blueprint to guide our design and development. So, this helped us to stay organized and reduce the confusion which might be caused during the implementation part. So, now my teammate Harshita will continue from here.
Establishing groundwork refers to the process of laying the foundation for a successful project management. In reference to Smart Campus project, we will need to identify the necessary infrastructure, process, and plans to ensure the project is executed efficiently. The first comes the identifying stakeholders. Stakeholders on Smart Campus include users such as students, faculties, and staff who directly benefit from the enhanced services and learning environments, and administrators who plan and maintain the smart technologies and infrastructure. Going to the next topic, recognizing multiple viewpoints involves acknowledging that the diverse smart campus stakeholders, like students wanting seamless Wi-Fi, faculty managers needing energy efficient and data privacy that might have conflicting priorities. So we have to identify different viewpoints in order to implement a good project. Now, coming to working toward collaboration means actively integrating these needs through shared governance and technology platforms to achieve a holistic and mutual beneficial campus environment. Next topic is eliciting. Next comes the first questions. Always we need to ask questions so that there is a better understanding of the project, like what is the vision of the smart campus, what technologies are included like IoT, AI, cloud, data analytics, what are the user requirements and expected benefits, what is the budget and timeline and the risk tolerance, and how early the project has to be completed and implemented, how will data privacy and security be maintained. These are the questions that has to be asked in order to understand the project and have a seamless workflow. Coming to the next thing, that is eliciting requirements for smart campus. Collaborative requirements gathering is the first thing that we have to look in this. This involves capturing the subjective needs of the stakeholders and translating them into clear technical specifications. The quality function deployment is a method that is used to formally map the voice of the customer to the measurable design features. QFT's primary output, the House of Quality, helps prioritize each smart campus features that should be developed first based on their potential to maximize stakeholder satisfaction. We have three different types of quality functional deployment, that is the normal requirements, The expected requirements are the requirements that are implicit to the product or system and may be fundamental that the customer does not explicitly state them, but their absence will cause a significant dissatisfaction. Next comes the exciting requirements. These are the features that go beyond the customer's expectations and prove to be very satisfying when present. This exciting requirements enhances the project. Next comes the usage scenarios and elicitation work products. Usage scenarios are simple stories that illustrate a specific interaction between a user and the smart campus system to achieve a goal. A key scenario is a predictive maintenance where the sensor detects a failing asset, automatically triggering a work order before the system breakdown occurs. Elicitation work products are the resulting documentation, including a formal requirement specification document, the stakeholder analysis, and user stories written from the user's perspective. These are the usage scenarios and elicitation products. Next will be continued by my teammate Mohit.
Developing use cases. Developing use cases helps us understand how a smart campus system works. We start by identifying the main actors such as students, faculty, admin, and IoT devices. Then we define key functions such as smart attendance, parking, energy saving, and security. Each use case includes the actor, goal, steps, and final outcome. For example, in smart attendance, a student enters the class, the system detects their ID, and attendance is recorded automatically. These use cases makes it easier to design, simulate, and test the campus system. Building the requirement model. Building the requirement for a smart campus simulation involves clearly defining what the system should and how it should perform. We begin by listing functional requirements like smart attendance, parking, energy, control, and security, along with non-functional needs such as accuracy, speed, and reliability. Then we identify the users and data the system will handle, as well as any hardware or IoT devices required. We model system behavior by defining inputs, outputs, and use cases. Finally, the requirements are linked to system modules and validated with stakeholders to ensure clarity and correctness. Next topic will be continued by my teammate Mukund.
Thank you, Mohit. Now, hello everyone, my name is Mukund and I'm here to close the requirements engineering chapter. Mohit has shown us the model we wanted to build. My job was to make sure that the model was actually buildable. This brings us to negotiation. And let me be clear, in our project, negotiation wasn't a conflict. It was a productive conversation between our team, our mentors, and the faculty. We knew what was technically thrilling, like full sensor automation and advanced Raspberry Pi integration. But we had to achieve the perfect balance within our limited timeline and available hardware. So we defined our win conditions clearly. Our system had to be functional, secure, and elegantly simple to demonstrate. By facing these trade offs head on, we didn't compromise our vision, we focused it. This rigorous negotiation process ultimately allowed us to lock in realistic goals and forge a project roadmap that was solid, clear, and ready for execution. So this is how we negotiated our requirements. Now let's see how we validated them. Once we had our final negotiated goals, the next critical step was validation. We can't build a project on assumptions, right? So we treated every requirement like a hypothesis. Is this realistic and can we actually test it? This meant confirming critical functions, like will the motion sensor reliably and instantly trigger the lights? Or does the smoke detection system trigger the alarm with zero false positives? Crucially, every single function had to perfectly align with our overarching mission, building a truly safe and automated smart campus model. This validation step was our final quality check. It confirmed beyond a doubt that our entire project plan was not only technically feasible, but also perfectly aligned with the high expectations of our stakeholders. So we had the green light to build. With the requirements secured and validated, we are now ready to fully model our system. To take us into deep analysis of those validated requirements, I'll hand the presentation over to Amog.
Okay, coming to requirement analysis, it's one of the most important phase in building a smart campus system. First, we begin defining the campus needs and objectives. This means understanding what problems we want to solve and what goals the smart campus system aims to achieve, such as improving efficiency, convenience, and sustainability. Next, we identify the key stakeholders. This includes students, faculty members, administration, anybody who's involved in the project, basically. Each group has different expectations, so their inputs are essential to design a balanced system. Then we collect user requirements and system requirements through surveys, interviews, or observation. This helps us understand both what the users need and what the system must technically support. The requirements are divided into two main categories. Functional requirements, these describe what the system should do. For example, features like smart attendance tracking, IoT enabled classrooms, and energy management systems, and so on fall under this. Coming to non functional requirements, these describe how the system should perform. This includes aspects like security, scalability, and reliability, which ensures the smart campus remains safe, can handle growth, and operates consistently. Finally, we produce clear specifications that guide the design and development of the smart campus system. In short, requirement analysis ensures that the smart campus system aligns perfectly with the needs of all the stakeholders while maintaining high performance and stability. The next topic will be continued by my teammate, Shreyas.
Now let's talk about scenario-based modeling. While our class diagrams show the structure, scenarios show the behavior on how our systems actually work in real-life situations. It describes how users interact with the system through concrete step-by-step examples. The key components are actors, which are students, faculties, or IoT devices, use cases, which are specific tasks like marking attendance or booking rooms, and other scenarios, which are the detailed flow of what happens step by step. We model three types of flows. Normal flow is when everything works perfectly. Alternative flow shows different valid paths to achieve the goal. Exception flow handles errors and unexpected situations. It helps us validate our design with stakeholders who may not understand technical diagrams but can easily follow scenarios. It identifies the problems we might miss otherwise, and it also gives our testing team ready-made test cases. Now, let me show you some real-life examples from our smart campus in the next slide. Here are three real-life scenarios from our smart campus project. Scenario one consists of automated attendance. The most common use case, a student approaches the classroom and taps their RFID card. The system validates their ID and checks if they're enrolled in this course, and marks the attendance with a timestamp. The occupancy sensor updates the room count, and the system automatically adjusts the temperature based on new occupancy. If the card is invalid, then the access is denied and an alert is sent to their phone. Scenario two is a smart environmental control. This runs continuously and the temperature sensor detects it's 28 degrees, which is too warm. Occupancy sensor reports 45 students are present. Therefore, the system calculates the optimal temperature, which has to be 22. For that, the occupancy and the command and also commands the HVAC system to adjust the temperature. Light sensors also adjust the brightness automatically. If any sensor fails, the system switches to safe default settings and notifies the maintenance. Now coming to scenario two, which is classroom booking. A faculty member logs in, selects their preferred date, time, and capacity. This system queries the available rooms and displays the options with equipment details. Faculty confirms the booking and the system updates calendars and sends confirmation. The important point is that all these scenarios work together using the classes that we designed: student, course, classroom, and the sensor classes, which integrate to enable these real world use cases. This combination of structural modeling through classes and behavioral model through scenarios ensures that our smart campus works seamlessly in practice. Thank you. And now the next slide will be explained by my friend Nityash.
Thank you, Suresh. Before moving into data modeling, I want to quickly explain the UML models that supplement use cases. Use cases are great for capturing functional requirements, but sometimes a text-based description is not enough, especially when the scenario involves decisions, multiple actors, or different states of operations. That's where UML diagrams help us by giving a clear visual representation of how the system behaves. The first model is the activity diagram. It provides a graphical flow of interactions within a scenario. It looks similar to a flow chart and uses rounded rectangles for actions, diamonds for decisions, and arrows for flow, and horizontal bars for parallel tasks. In our Smart Campus project, this helps us visualize how the motion sensor detects movement, sends the signal to the controller, and triggers the LED or fan to turn on for a specific duration before switching off automatically if no further motion is detected. The swim lane diagram is an extension of this. Each lane represents an actor or analysis class, making it easier to see who is responsible for each action. For example, One lane can represent the motion sensor, another the controller, which is the Raspberry Pi, and another for the appliance like LED or fan. This clearly separates responsibilities and shows the overall interaction among system components. The sequence diagram shows how messages move between objects over time. This timeline flows vertically, and messages between lifelines illustrate how an event travels from one component to the other. In our case, when the motion sensor detects movement, it sends a signal to the controller, which processes the event and then sends the command to the LED or fan to turn on. After a set time of inactivity, another message is sent to turn off the appliance. Finally, the state machine diagram shows how a system or object changes its state based on events. It focuses on the life history of the component, what states it can be in, and what events can cause transitions. For the motion sensor scenario, the state could be idle, motion detected, active, and idle again. Similarly, the connected appliance may move between off, on, and off states based on the sensor input and timing conditions. Together, these UML diagrams provide visual clarity and strengthen the use cases. They help us identify missing logic, ensure every interaction is accounted for, and make the overall system behavior of the motion sensor setup easy to understand and validate. The next part will be continued by my teammate Dave.
So data modeling is basically the process of organizing and structuring the data so the system becomes consistent and easy to manage. It is done in three levels. First is conceptual level, and second is the logical level, third is the physical level. We also use UML cases diagrams to show the data security, data structure visually. A class contains class IDs like sensor ID and type along with functions like collect data. Overall data modeling helps us make the smart campus system more organized, scalable, and accurate, especially when integrating IoT sensors data with student and classroom information. We are having some examples. The first is a conceptual data model. This is a highest level view and focuses only on the main entities of the system, such as students, course, classroom, sensors, and faculty. It also shows that these entities are related, like student to course bring many to many, or class to sensor being one to many. At this level, we don't worry about attributes or data types. We only are defining the data that exists in the system and how the major components are connected. Coming to the second model, this is a logical data model. This adds more structures by introducing attributes, primary keys, and foreign keys. Example, student will have attributes like student ID and department. Sensor have type, status, and room ID. We also define the relationships. For instance, the many-to-many student course relationship becomes enrollment table with the foreign keys. Finally, in the physical data model, we have the actual SQL tables used by the database. Here we specify the data types, constraints, and exact table structures. For example, student ID becomes the INT primary key, course name becomes varchar 80, and foreign keys are defined between the tables. Together, these three models move from a simple and high-level conceptual view to a full defined database structure ready for implementation. They make sure that our smart campus system is consistent, scalable, and easy to manage. Now, my friend Raman will continue.
Hello everyone, I am Raman and I will be explaining class-based modeling in context of our smart campus project. It is an object-oriented approach. A class is a blueprint for creating objects that share properties and behavior. For example, all students are unique, but they share common data like student ID, name, email, department, and year of study. So we define student class instead of repeating data everywhere. Each class has attributes, data properties like student ID, email, etc. Methods, actions like enroll course. We use UML class diagrams to visualize this. Each box shows its attributes, methods, and relationships. The visibility symbols like plus for public, minus for private helps us to secure structured data. These diagrams keep everyone, developers, IoT engineers, database teams, aligned on the same design. Here we see some class-based model examples. Student class stores student details and methods like enroll course, mark attendance, and connected to IoT devices for attendance via RFID or facial recognition. Course class defines course ID, course name, credits, and has methods like add student, assign faculty. Classroom class has attributes like room ID, capacity, status, and methods like book room and control devices to manage lights, AC, and projectors. Sensor class tracks environment data, temperature, motion, CO levels, and methods like collect data, send alert, and help maintain safety and comfort. Relationship ties everything together. Student enrolls in many courses. A course uses one classroom per session. Multiple sensors monitor one classroom. This design ensures reusability, easy maintenance, and scalability. If we were to add any other features, they plug right in without redesigning everything. Finally, our UML class diagram combines everything, showing how teachers, courses, classrooms, and sensors interact. Each team uses it differently. Developers implement these classes in code. Database admins turns them into tables and relationships. IoT engineers know what data format to send. Testers verify that each method and link works correctly. For example, when student enters LH101, their ID triggers mark attendance, occupancy sensors update the count. All of this happens smoothly because of strong data modeling and class-based design. Next concept will be explained by Nidhi. Thank you.
Now we have the final chapter of this module, which is requirement modeling strategies. So why do we need these? These help better understand the system's view and how various actions trigger different responses. These are add-ons to the class-based models, UML models, and scenario-based models. So we have two types, flow-oriented modeling and behavioral modeling. Under flow-oriented modeling, we have data flow diagrams and state diagrams. Data flow diagrams are further divided into three types, level 0, level 1, and level 2, each more complex than the previous. State diagrams are level specific and help the developer understand how the system responds to various events. Behavioral modeling, under behavioral modeling, we have sequence diagrams, which shows how events cause transitions from object to object. So this is a level 0 DFT for the smart campus simulation. We have our website from which the user gets commands and data. We have the sensors, which give sensor status, the smart campus software, which eventually controls the lights and the fans. Next slide. So this is a level 1 DFT, which is a further breakdown of the smart campus software. So we can see that the website here, it interacts with users where you're supposed to give password, where you're supposed to give various defaults for lights and fans. We have two-factor authentication. For sensors, we have monitor sensors, which in turn control the lights and the fans. So this is a level 2 DFD, which deals specifically with the monitor sensors bubble. So the sensors here, what sensors can do, they can read. Then based on whatever defaults have been given, they decide whether to change the light controls or the fan controls. All of this is done under the monitor sensors part. Now, state diagram, it shows us how the system responds to various events. In this case, we will take the event of lights. Here we can, if you see in the reconfigure part, you can set the light intensity, what is the lowest point you want, what is the highest point you want. And then once it shifts to the idle state, that time it will start monitoring the motion detectors and the light intensity sensors. Motion detectors decide when to switch on the lights if people are in the room. And then again, the intensity, it checks if it is within parameters and accordingly switches the intensity. Once the people leave, the lights can be switched off. So now in the behavioral modeling, we have a sequence diagram, which shows how events transition from object to object. We have a user who enters the password, and the password is compared to what is previously saved in the database. We have two-factor authentication. If the authentication fails, then the system is in lockdown and the user that is trying to access the website is prevented from changing any details. If the authentication is correct, then the sensors are activated and the user sees the output accordingly. So that was a complete breakdown of the SEPM module 2. Thank you.